Okay, I guess you can hear me. Hi there. So my name is Liviu. I work for Google. Prior to that, I've been working for Fitbit, which is now part of Google. And today I am going to present you a small, simple and elegant solution of how to mitigate flaky tests in your production development. So first of all, what is the objective of this presentation? I'm going to present you a very simple and elegant machine learning solution that could detect flaky tests and save you time, save resources for the company, and also save you a lot of nerves. The overview is very simple. I'm going to present you the problem, what are flaky tests and why they are so bad. Then, once we know why flaky tests are bad and why they are so wasteful with our resources and our time, the next natural question is, what do we want? Obviously, we want something that could help us out so we don't rely on wasting resources to get over those flaky tests. Then we're going to present you a solution, this machine learning solution that we have in place. And then we're going to show you some nice results. And basically, that's it. So before we dive right in, I want to make sure that, so there is a lot of public research done on the mitigation of flaky tests. This is done mainly by Google. There's an hour-long presentation by GTAC in 2016 on how flaky tests, how to mitigate flaky tests in continuous integration. There are also 2 blog posts. Feel free to read them. They are very lengthy and they provide a lot of details that I may not be able to provide in this presentation, but I'm trying to do a sketch of those. And our solution is also based on that. So our solution was developed at Fitbit while we're not part of Google, and then Google came. So first and foremost, the problem. Before we address the problem, can you show me your hands? How many of you write tests, and why do we write tests? Okay, and why do you think we write tests in general?
So we make sure we don't screw up when we bring in new features, changes.
Great. Yeah. So this is a list that I will provide. It has like 4 points. It's certainly something subjective. There is no like agreed upon reason why we write this. I think primarily is because we want to write better code. The idea with testing is that it's better not to trust your own code. So usually when you write a piece of code, it's not okay to just release it right there in production. Also, I mean, you can write a piece of code that runs as you want it right from the first shot. I mean, there are two conditions in which that could happen. I mean, either the thing that you want to write is very simple, or you are a genius. So I would assume most of you work with code bases that are not simple, and you have to write code that is not necessarily trivial. And I would also assume that, I mean, hopefully all of you are geniuses, but usually the probability of some of us being a genius is very low in general. So it's better not to trust the thing that you write, so it's better to write code, to write tests, because usually when you start to write tests, you're gonna find a lot of bugs on your code that you've just written. A second reason why I think we write tests is because of easier debugging. Now, of course, if you have a very small project, you can just debug it in the IntelliJ or whatever IDE you are using. But if, for instance, you have to write a microservice that depends on other microservices and also has a database, I mean, how are you going to debug that? I mean, you can technically deploy it into a, let's say, a non-production environment, and then you do some manual testing, like you do some REST APIs or whatever, and see what it comes out of that. But that's pretty time consuming, and I mean, yeah, you can do printf type debugging like that, but it's not productive. With debugging, irrespective whether it's JavaScript or Java or whatever, you're gonna have a testing framework, and that code is isolated in that sandbox. So you're gonna see exactly the code that you wanna debug. So it's easier for that. The third reason is, yeah, I've added this one, although yeah, there's a lot of controversy with that, which is to measure progress, and by progress I mean test coverage. The rule of thumb is that the more the better. Although, as I said, this is a controversial topic because higher coverage doesn't necessarily mean that you have no bugs in your code. I mean, you can have 100% coverage. That doesn't mean you don't have any bugs in your code. But anyway, the point is, it's a good measurement. I mean, if you don't have any test and you don't have anything to measure, you don't know. I mean, there's a high probability that your code is complete crap, so to speak. And of course, the fourth reason I would say, which is in many ways related to the first one, which is release with quality. Of course, if you write a piece of code, the question, I mean, think about it this way. If you have, let's say, you are working for a web application that serves, let's say, tens of millions of users. So you have to write a piece of code and you have to deploy it in production right away. Without any tests, how many of you are confident you can just do it without any tests? So yeah, maybe not that many. Unless that change is extremely trivial, like some small config or something. But even in that case, you are still like kind of afraid to do deploy in production right away. So once you have tests, you are at least partially confident that you can deploy things in production. Yeah, so release with quality, and I should have added that, release with quality and confidence. So at least you have some confidence that maybe it won't break right exactly as you deployed it. Before, again, we dive right into the problem, how many of you are familiar with this type of diagram, with a CI/CD architecture? Raise your hand if you, okay, quite a few. Yeah, so basically I've divided up this picture into three parts. So there's the code development where you push your code to a source control management. I've added GitLab here, but it could be anything. It could be a Bitbucket or whatever other code management like that. The way this type of CI/CD infrastructure works, and I'm sure a lot of you know, is that the source control management, in this case GitLab, will just trigger a build in a continuous integration platform. Here we have Jenkins, but it could be anything. It could be, I don't know, TeamCity. There are quite a lot of platforms like that. I've added Jenkins because that's kind of like the lingua franca for continuous development. And what usually Jenkins does is, in this case, it tries to, I mean, apart from some like basic stuff like check styles and stuff like that, it usually runs the tests for your project. And if those tests pass, it will usually create a build, and that build is stored in here down in Artifactory in a build repository. Again, I've added Artifactory, but you could have like Nexus or any other build repository like that. And then the third part, the blue part of this picture, which relates to the deployment. So once you have a build, which could be a Docker, it could be a Docker image for a web application or a microservice, or it could be, let's say, if you're doing mobile development, it could be an APK file for Android development, what have you. Once you have that, then you deploy it. Here, that usually pertains for web development and backend development, where usually you deploy Docker images or Docker containers in a Kubernetes cluster. But again, it could be anything. It could be a Mesos, it could be a Marathon, or whatever, any other scheduling system like that. So the rule of thumb for this CI/CD architecture is that you want your test to pass because otherwise that would block your deployment. So if you have, for instance, you want to do a deployment in production, which is very urgent, but then you have one test that is failing, right? So you cannot do the deployment. So what you should do in that case? I mean, ideally, you should look into the Jenkins log and see which tests are failing and fix them, right? That should be the natural flow, especially if the test that is failing is highly related to your particular code change. But what happens? Let's go to the next slide. What happens if you have a test? So, for instance, you push some code, then the source code management triggers a build in Jenkins, for instance, and you have a test that failed, and it could be a test that has nothing to do with your particular change. And the reason I'm saying that is because unless you have a very simple project, which is just one project with a few files, but in general, in many companies, we all work with very large code bases, which have like hundreds of thousands of lines of code and probably thousands, if not more, tests. And that code base is usually split up into smaller projects, and each team owns one or a few projects in that particular large code base. So let's suppose you run this Jenkins and you have a test that is in another project that fails, which you don't know what to do with that test. It was probably written a few years ago. So what are you gonna do? I mean, naturally you'll assume, yeah, maybe it was a network issue or something like that, and you're gonna hit the rebuild button. And let's suppose that you hit the rebuild button, the build will start again the second time, and that particular test that failed initially passed, but now other tests are failing. And you assume, well, maybe there is something wrong with the infrastructure, and then you hit the rebuild button a third time. And the first test that failed and then passed on the second build now is failing again. So you have this sort of like random behavior that some tests are usually exhibit. And you don't know exactly why. And most people would assume there's some networking stuff, or maybe the way Jenkins and other build systems like that run their tests is that they sort of run their tests on some machines on a cloud. And you could assume, okay, maybe that machine, that virtual machine crashed or restarted or whatever. So let me do a rebuild again. Okay, so what I've just described is basically a flaky test. Now, whether it's because of a network issue or a virtual machine crash or whatever, this is a flaky test. And the problem with that is, if you have a very large code base and you want to do a rebuild, a deploy in production, I mean, again, if you have a very small project, that might not be such a big problem, but for many of you that are working in large companies and are dealing with large code bases, sometimes a build like that could take an hour. I mean, when I've joined Fitbit in 2018, our whole build was taking like 2 hours. So you cannot wait 2 hours and see a test or a few that are failing and then hope it was a networking issue and then do a rebuild again. It's a lot of waste of time for you, and after a while, it's not that you are going to be slightly frustrated. I mean, you're going to be sometimes downright mad for that. And on top of that, there's also waste of resources, right? I mean, all those machines in the cloud, I mean, they will just run the same thing over and over again, hoping that it will pass eventually. So this is a flaky test, basically. So yeah, what is a flaky test? The proper definition is a flaky test is a test that is observed to fail and pass on the same code. On the same code, meaning the same code that you've introduced in that particular pull request or Git revision, whatever. Now, why they are bad? I think I've already explained that. So yeah, because they are a waste of valuable time. But there is another hidden reason why they are so bad. And the reason why they're bad is because if you experience this type of intermittent behavior over and over again, you kind of lose your confidence in testing in general. You feel like, okay, I did my work, everything works, but now I have to do the deploy in production. So you kind of get a little bit frustrated because you know a lot of tests that are not related to your change will fail. So you have to you have to either try to change that yourself, but that's not going to work very well. I mean, you would just rebuild until it will probably pass, or in some cases you could get some sort of a SRE exception for some of those tests, so you can just deploy it with even though tests are failing. But again, that's not a very good idea. So The reason is that you lose confidence in tests, and once you lose confidence in tests, that's a very bad spot to be as a company or as a team, because sometimes some of those tests can fail because of your actual code that you've introduced, but you're gonna ignore that because, okay, maybe there's something with the infrastructure, or maybe there's some old tests I don't know, so I don't care. I'll just do the rebuild, and eventually, hopefully, after a day or two, I could get my deploy in production. Although I'm late, but you know, a day or two wasted. Uh, so what's the best approach? So what's the best approach that we had when we've encountered this problem? So I think I've already explained that, which is the rebuild button, and finger crossed or praying to whatever God, hoping that they will pass this time and we're gonna get something in production. But obviously that's not something. It's not something you want to deal with, obviously, especially especially in terms of productivity. You're gonna waste actually a lot of time just for that, and that's valuable time that you could use for something else. Uh, so, what are the causes of those tests that become flakes? Yeah, we call them flakes. I mean, flaky tests, flakes, or non-deterministic tests, whatever. Uh, there are, roughly speaking, two types of reasons why tests become flakes. The first one is programming causes. This is very common and is fixable. Contrary to this is kind of counterintuitive, because you would assume that if a test fails and passes, it's because of some networking stuff. That's sort of like the first intuition that you go through. But that's actually not the case. I mean, yes, infrastructure could be flaky as well, but hello. No. But in general, the reasons are programming related. The reason is usually people have written tests over time, and it's what is usually known as technical debt. Uh, there are basically several programming reasons, and I've listed them here. So by far the most common is asynchronous behavior. So whether you are doing mobile or backend or web development, whatever, asynchronous behavior is kind of like the norm. You cannot really escape it. One way to summarize asynchronous behavior is this, which is thread slip. This is obviously in a Java context, but it would work in a Python, Golang, JavaScript context as well. So usually you are waiting for something, but that something is asynchronous, basically. So the combination between those is usually the most common reason why tests become flaky. Another one is unclean state. That's also very common. It's rather simple to fix it. And it goes like this. You have a file and you first develop a test, okay? So you have some sort of a global state where you add something for that test to run. Kind of like a before run test or something. But it's not a before run, it's just it's like a global variable or something. And then somebody else comes along and adds another test. And they add whatever data or state to that particular global structure without realizing that they need the previous structure that was initialized by the first test. So once you have, let's say, a bunch of tests like that, they will usually pass if you run them all at the same time. But if you run them in isolation, they usually fail, because if you run a test in the middle, it will fail because it needs something that was initialized in the code of the previous test. So that's very simple to spot and very simple to fix. But you would be surprised, it's quite common sometimes. The third one, which is by far the hardest, but fortunately is not that common, which is synchronization. So for instance, is when you have complicated integration tests where you want to test some sort of like communication between two pieces of code. So usually start two threads, for instance, and race conditions usually happen because you don't take the proper measures to do some proper synchronizations for those data structures. So I would say race condition in this particular category is by far is probably the only reason. as I said, race conditions are notoriously hard to find, but fortunately, in testing at least, is not that you don't find that many flaky tests that have synchronization issues. The fourth one, which is very common and is by far the most annoying, and also the most hard. I mean, it's easy to fix, but it's also hard to spot, which is time-based constraints. So usually a test is assuming a specific date or time. So for instance, you have a test that is trying to rely on a particular date and time, but it doesn't take, for instance, time zone into consideration. That was a case. So it runs here in Bucharest, but it doesn't run on Jenkins, which is in a cloud in US because it's a different time zone. So that kind of stuff. These are very annoying, especially because it fails on Jenkins, but then you run it locally and it passes. And you can always reproduce that type of behavior where it fails on Jenkins but runs locally, and you don't know why. You feel like there's something very weird going on. And of course, the second cause for flakiness are obviously external causes, which I've just discussed. So it's not that tests are flaky. Sometimes the infrastructure could be flaky as well. There are broadly two reasons. One of them is virtual machine crashes, as I said. So Jenkins usually runs those tests in some machines somewhere on the cloud, and there might be an update, there might be a crash. Maybe the SREs for that team decided to do a restart for those machines for some maintenance or something. These are very easy to spot, basically. I mean, once the machine reboots, then everything is fine. Or you do the rebuild and the test is allocated to another machine in the cloud, and that's problem solved. And of course, networking issues. And in many ways, networking issues, these are very hard to spot, and usually networking issues are what usually lead to asynchronous behavior flakiness in general. And we will see in the moment why. Now, there's a lot to unpack here. I'm not going to show example of each of those causes because that would take a lot of time, but I'm going to show you just one example of a simple asynchronous behavior flaky test. So this is not a real test, okay? It's sort of like a pseudocode here. So what we have a for loop in this test where we post this message called test 10 times, and we post it to this Kafka topic. And this method post message is asynchronous, meaning that it doesn't really wait for that to be posted, it just returns immediately. Then we wait for 1 second, right? We hope that once the for loop executes, then we wait for 1 second, hoping that in that 10-second time frame, all the messages are posted to Kafka topic. For those who don't know what Kafka is, I mean, it's just like a distributed queue. A queue. And once we waited for 1 second, then we do an assert, and we check whether we had those messages in Kafka, in that Kafka topic posted, and we check if there were indeed 10 messages posted. Now, that usually should work. I mean, posting a message like that should take a few milliseconds, or let's say a dozen milliseconds, something like that. But if there is some networking issue for some reason, whatever, there is a possibility that because this is an asynchronous call, it might not, after 1 second, only 5 messages were actually posted to that Kafka topic, or 6 or something like that. And then when you do the assert, you're going to see that, okay, the assert will fail because you have just 5 messages instead of 10. And quite possibly you're going to run this test again and it will pass, for instance. And then you run it in Jenkins, for instance, and it fails again for some reason. So that's usually the most common way flaky tests usually, the most common way tests become flaky. So now that we know what a flaky test is, the natural question is how are we gonna solve for that? the obvious way to solve for that is just look on those flaky tests and solve them, right? I mean, uh, you you see the test. I mean, if thread.slip is the most common cause, I mean, why not do a control F and search for thread.slip in the testing directory and find all of them and see if they're flaky and just fix them? Well, actually, that's easier said than done, right? Because if you have a large code base with thousands of tests, and quite possibly you have JavaScript tests, you could have like Swift tests, for instance, if you have a mobile application. You could have, even if you have just a repository with backend services, you can have like 10 or 20 backend services, and they have a lot of tests, and you don't know the logic that goes into each of those microservices. So uh, fixing them right away, it's not really doable unless you have a lot of time. The other thing is, uh, yeah, I wanted to say something, but I think I forgot. uh, Another thing it would be because you have a very large code base and that code base is split into projects, so you have teams that own different projects, so you have an owner's file for each of those projects. You could poke developers from those particular team. Hey, you could solve your flaky test. Uh, so that would probably do some sort of a balance. So every team could solve their own flaky tests. But again, that's easier said than done as well, because just think about the time example that I gave you. So you go to a colleague of yours in another team and you say, look, you have this test that is failing. Okay, let me see where it's failing. And he or she runs that test locally and it passes. So where's the problem? I don't see any problem. Maybe there was some networking issue. I mean, try it again. I don't have time for that. Plus, in this agile world that most of us live, you just don't have time for this kind of stuff. I mean, you have things to do in the sprint, you have things to release. You don't have time to look too much into those tests. And especially, I mean, if there is a real failure, so if there is a test that fails all the time, that's a real failure. So that's very easy to reproduce. But because flaky tests are not reproducible, sometimes they are, sometimes they are not, people don't perceive them as an actual problem. They usually, from an intuitive point, they just intuitively go to, okay, it's a networking thing, it's an infrastructure thing. My tests are okay because look, I ran it locally and it worked. So we reached the end of some sort of end of the road here, where okay, we know what flaky tests are, we know how bad they are, we know how they can cause a lot of frustration among developers, and we also know that they waste a lot of time and resources, so they're pretty bad. So, what do we want? Well, obviously we want to we want to solve it, but the question is how exactly going to solve it. I mean, ideally, instead of just poking people around in the team to hey, fix your test, we want to have some sort of a tool, ideally, that could automatically detect those flaky tests and tag them accordingly. Or at least we know these tests are flaky, so we can just do an ignore or something like that, at least for the moment. So now that we know what we want, how are we going to solve that? So let's go right into the solution for that. So before we get into the nitty-gritty of machine learning, first of all, we have to develop some intuitions about flaky tests. So basically, we have three types of intuitions regarding flaky test. The first one is we can look at the test execution history. So obviously, as I've just said, so if a test fails and then passes and then fails and then passes, so if you look at that test execution history over a certain period of time, you know there is something fishy going on right there. I mean, either it fails like in successive revisions or passes in successive revision. But if it fails and then, let's say, fails and passes and then fails again and then passes, and so there's something wrong there. Another thing that we want to look on is the relationship between the code and the test, meaning that the relationship between the code that you've changed and the tests that are running. So uh, obviously, I mean, the intuition here is also relatively simple, that if you change something in project A and you have some tests in the same project A that are failing, there is a high probability that those tests are actually a real failure because of your change. But if there are some tests that are failing in a completely different project, maybe there is a possibility that there's a problem with those tests and not with your code. Uh, another intuition is, believe it or not, source file type. So there's a lot of pull requests in the Bitbucket or GitLab jargon. We have a lot of pull requests where you change just a few config files, like a Gradle or a build file, and still you have tests that are failing. And of course, that doesn't necessarily mean that if you change your config files, you expect that tests should not fail, because maybe you changed some configuration that those tests depend on, so obviously your test will fail. But in general, if you change non-code files and you still have test failures, maybe there is something fishy going on over there, and maybe you should look into that. I said 3, there are actually 4 intuitions, but sorry. So the other thing, the 4th one, or the last intuition, is file modification history. So what does that mean? It's common knowledge that the more you change a file, the more bugs you're going to have because of that changes. So if you have a particular file in, let's say, a core library that has been changed by a lot of people, or has been changed by just one person that has done, let's say, 100 commits on just that file, okay? There's a high probability that there's a lot of bugs over there, and maybe the tests are failing because of those code that you introduced. So let's develop this, let's look on all these 4 intuitions one by one. So let's start with test execution history. So the intuition here is that flaky tests fail and pass over time on multiple revisions. Of course, by revision, you can replace the word revision with pull request. So once you do a pull request and you merge it into master, that would be that revision where the pull request merged into master. So we have this concept called edges, and basically it goes like that. So let's suppose we have this test here, some service test, which is in this project. And here we have the history of the execution history for this test. So we see that this test has passed on this. I mean, CL comes from change list if you're in a SVN type of environment, but it could be like git revisions on the master branch in CI. So this test has passed on the first revision, and then it was ignored on the following 2 revisions, and then it failed, and then it was ignored, and then it failed. So if it passes and then fails, we call that a negative edge. If it fails and then it passes, eventually, we call that a positive edge. So why do we do that? It's because of this. The intuition here is that a test that has many edges like that, positive and negative edges, this is a strong signal that that test is flaky. There is something wrong with that test. It's not the infrastructure, it's not the a Jenkins machine in the cloud failing. There is something with that test. So we see here that on this 5-hour period, test 2 has a lot of failures and passes, whereas the second test has just 1 failure and 1 pass. So the first test is highly likely to be flaky, whereas the second one could be, or it's more likely that it's not flaky. The second intuition, which is the relationship between the code and test. Usually in a large code base where you have a lot of projects and libraries and that kind of stuff, you tend to develop, to define dependencies between projects. So for instance, we have here microservice A, which depends on core library 1, which in turn depends on logging library. So for instance, if you introduce a change in logging library, which is the green circle over there, and you have a test that is failing in the same logging library project, well, the distance is basically 0. So the test is failing right at the project where you introduce the change. But if you introduce a change and you have a test that is failing in microservice A, for instance, As you can see, there's a distance of 2 in terms of transitive dependencies. So the farther a test that runs fails with respect to your change, the higher the probability that that test is flaky, basically. The third intuition, which is source file type, and it says that test cases that fail due to changes in config files are very likely to be flaky. As we said, by config files, we mean everything that is not code, like Java, Swift, what have you. And we see a lot of pull requests, PRs, pull requests, where the only changes are done to Gradle, XMLs, JSONs, or even text files. I mean, right now, if we change the text files, it won't trigger the test, but we used to have that. Anyway, so changes to config files that still trigger some tests to fail, that's a strong indicator that that test is flaky, and there's something wrong with that test. And of course, file modification history, which is divided into 3 things. The first one, as I said, is frequent file changes. So the file modification history, these 3 intuitions usually refer to real test failures rather than flaky failures. So if you have a file that was changed a lot by one author or by many authors, in that particular revision where a test has failed, it basically means that probably that test that has failed is a failure and not a flake, because that file has been changed a lot. The same goes here as well. File changed by multiple authors. So that's basically the same as the first, but we divided them into 2 because, as I said, you can have a file that has been changed by one author but many times, or you can have a file that was changed by multiple authors with just one commit over a period of time. So we account for the 2 metrics here. And of course, usually we like to keep our pull requests as small as possible, not too many files. But it so happens that from time to time there are some pull requests that have like a lot of files, like sometimes even hundreds of files. So obviously in that case, if you have too many files in a pull request, and you see test failures, probably that test failure is a real failure and not a flake. It's probably you introduced something wrong over there. So before we move on to the next slides, where we're gonna deal with some of the machine learning, we're gonna have like a high level view of the machine learning that we've developed. Basically, what we want. In terms of machine learning, we're gonna do 3 things here. We're gonna do what is called futurizing. So we're gonna get all this data from the test execution history, and we're gonna create some features. Then we're gonna pick a model. Now there's a lot of debate on what kind of model you want to pick. I mean, there are several models. All of them could work just as fine. We decided to go just with a simple autoencoder. And then we're going to do some training with the data that we've just collected. We're going to train that model, and then we're going to get some result. I mean, cat, not cat. So let's start with selecting the features. So many of you are probably using Bitbucket and GitLab or stuff like that. So obviously those platforms, they do provide an API where you can look for the Git history for a file, even for like for all the changes for a file in the last year. You can look for all the pull requests. You can look to see how many files were in a pull request that was merged and so on. Besides that, there is another thing that we have that we didn't mention, and I think a lot of you have that in your companies. But I think GitLab provides that as well, which is sort of like to have a database of all the test execution history for all the tests in your Jenkins repository. So basically, what we do is for each test case in the code base, we're going to get all the failures for the last 3 months. I mean, why 3 months? Because I think 3 months is a good enough period of time. You could have like 1 month, 6 months. It's up to you. I mean, there's no hard limit on that. So we're going to get all the test failures, all the failures that we experienced in the last 3 months. And then for each failure, we're going to compute a feature vector that will include some of the information that we've just discussed, some of those intuitions that we've just discussed. And what are those? So we're going to count the number of pass and fails between different revisions. So for instance, for a failure, we're going to look back in time and we're going to see, okay, so this test failed here and then passed and then failed again and passed and so on. So we're going to measure only those differences between failures and passes, when it actually transitioned from failure to pass or from pass to failure, what we call an edge. And then we're gonna look for all the files that were committed in that particular revision, and then we're gonna look for all the authors that committed for each file in that revision. Of course, we set a hard limit of 50 files. On average, there are something like 10 files per pull request. There are some very rare pull requests with 100 files, but those are usually rare. I mean, if you have 30 files changed in your pull request, that's still like a lot of files. So we set a hard limit of 50. We're going to look for all the files that were changed in that particular pull request, and we're going to count the number of authors for each of those files. And then we're also going to count the frequency of commits for each of the file in that revision in the last month. So if you change the file, then we're going to see how many times that file was changed in the last month. Again, last month. I mean, it could be 3 months. It could be we try with 3 months. We try with 6 months. Is the same. I mean, the logic here is that you need some history. Doesn't matter how big that history is. And then we're going to look at the ratio of config files versus source file in that particular request that was merged when the test failed. And then we're going to compute, that was the hardest part, we're going to compute the dependency distance between the project of the test case, of that test case that failed, and the project for the files where those files were changed. So to go back to the example with that small graph diagram, so if you change file A in a project and you have the test that failed, which is in the same project, then the distance is 0. But if you have a test that failed and is in a completely different project, you're going to measure that dependency because there has to be a dependency there. Otherwise, that test would not have run in the first place. And you're going to count that number, whether it's 3, 4, however far in the repository that project is. Okay, so this is what we have. Basically, what we ended up with for each test failure, we ended up with a fairly large array of numbers, which is the features that we're gonna use to train our model. And now to the nitty-gritty and the so-called cool stuff of machine learning. This is an autoencoder. We decided to pick an autoencoder as a model. Now, what is an autoencoder? By the way, how many of you have any knowledge of machine learning and neural networks in general? Okay, so yeah, quite a few. So an autoencoder is an unsupervised model where basically you try to you give an output, you give an input, sorry, and the output is basically the same. So you feed the data and the label is basically the data itself. So as you can see here, if you have this autoencoder, which is the classic autoencoder trained on the MNIST data set where you input images of digits from 0 to 9 and you get the reconstruction. The whole thing with the reconstruction in autoencoders is that there is a cost between the reconstructed image and the input image. So as you can see, the reconstructed image, that's the whole point with autoencoders, is not exactly the same as the input image, because otherwise if you train this autoencoder to reproduce the exact same image with the exact same pixel, that would be kind of stupid because it will overfit. So it produces an image very similar to the input image. That's what it's usually people call it generative AI. And I think you've heard that term a lot in the last months or something. Yeah, to recap here, after training the autoencoder, we'll be able to reconstruct the data that was given as training. So why do we need to have this autoencoder? What's the point with it? The point is that autoencoders are very good for anomaly detection. So anomaly detection is, I mean, the most simple example of anomaly detection is when you want to detect credit card fraud. Okay, so you have a bunch of credit card transactions which you know are clean, and you're going to train your autoencoder on that, and then once a credit card fraud comes along, that should have like a high cost. So that should be a strong indicator that is a credit card fraud. So how that translates to what we have here, we're going to train our autoencoder only on the failures and not the flaky test, and we're going to do that based on those simple intuitions. So we're going to collect only the test failures where a lot of files were changed and a lot of files were changed by a lot of authors and that kind of stuff. So we're not going to use for the edges, basically. Then the generated output vector is not exactly the same as the input, as we've discussed. So there are some differences, right? Those differences are usually called a reconstruction error. So if we go back here, there is a reconstruction error between this image and the input image. And if the autoencoder is trained well, this difference between the output and the input should be small, or as small as possible. Preferably not zero, because we don't want to learn the exact data set, but it should be rather small. So if we plot those test failures, those features for the test failures, we're gonna have and then we subtract the differences between the input and the output. We're gonna have some differences here, and they usually fall they fall below a particular threshold. Now, when we're gonna train, once we have our autoencoder trained, and we're gonna use flakes to input in our newly trained autoencoder, the feature vector for a flake is going to be rather large, or at least larger than for a known failure. So that would probably look something like that. So those blue points that you see here are basically the same points that were here. So as you can see, once you have the autoencoder trained on failures and then you input a flake, the flakes usually will have a high reconstruction cost. And the reason for that is very simple. I mean, an autoencoder, like any neural network, is a rather dumb thing. It's not as intelligent as people like to think. It usually learns the things that you give to that model, just like us humans, right? I mean, we learn only the things that we read. So when it sees something that it has not learned, doesn't know what to do with it, obviously it cannot reproduce that exactly. So the difference between the input and the output in this case would be large. So this is basically how we detect flakes. By the way, any questions? Is everything? Yeah.
So right now you're trying to predict whether a failed test is a flake or not, or what is the objective here?
The objective here is to, once you run it in Jenkins, you know it's a flake, and the way you do that, you take all that information from let's say Bitbucket, you take all that of history, all that test execution history, you create a feature model, you input to the newly trained autoencoder, and that will tell you if it is a flake or not, basically.
Okay, so you're trying to predict whether it's a flake or not.
Yes, exactly, yeah. And also the reason, I mean, maybe some of you might think, okay, why not just a simple classification?
Exactly my second question.
Right, yeah.
Because you already said that if you have a high number of fail pass, that already tells us a great deal. If you have 100 failed passes and one with 1 or 2, you can easily say that the first one is...
Right, exactly. In classification, so if you have a simple neural network where you want to classify pictures of cats and not cats, that data set has to be very well balanced. It has to be usually 50-50, right? Because if you have, let's say, 10,000 pictures of cats and just a few hundred pictures of not cats, Even if you input a not cat picture, it will still output a cat because the model will be so biased towards learning cat features and not other stuff. That's why we've used anomaly detection. Anomaly detection is basically a special case of classification where the majority of the failures are actually real failures. And there are some tests which are flaky. But in the greater scheme of things, there are not that many flakes. I mean, if you have 80% of your test flaky, then you do have a really big problem on your hand. Hopefully, that's not the case. So, most of the failures that you see are usually real failures. And because this data set is so unbalanced between real failures and flakes, you're going to have to train it on failures, and then what is not a failure is going to have a high cost, so that would tell you, okay, this is a flake.
And my third question is, why have you chosen an autoencoder when there are novelty and outlier prediction classical machine learning algorithms, not deep learning algorithms?
Yeah. The honest answer for that is it was pretty simple to code it in Keras, basically. And the other thing is that once you have an autoencoder, you can extend it in the sense that you can add more layers. For instance, you can play with a variational autoencoder, so you have more freedom to play out with those models rather than choosing a non-neural network model, so to speak. Does that answer your question?
Oh yeah, basically you are saying that because fewer hyperparameters.
Yes, exactly. Yes. So now let me show you some results. As they say, it's not much, but it's honest work. So this is what is usually called the confusion matrix. And the confusion matrix, I mean, it sounds like a mouthful, but it's not such a complicated concept. Is you take all the data that was all the test data, not the trained data, all the test data, and you see how, and then you look how many of them were predicted correctly and how many of them were predicted incorrectly. So. By the way, this is an old one. This is from 2019, I think, and we had like 802 flaky tests out of 19, 271 real test failures. Here, the confusion matrix shows us that we have a 100% prediction, but this is just for show off. In reality, is not. I mean, after after a while, it wasn't like that. So it was like 2%, sometimes even 5%. Sorry, 95%, 96%. So this is sort of like a show off, kind of like the first example that we ran through. Yes.
How did you label the flaky versus non-flaky? Did you manually label the 20 of them?
No, as I said in that intuition, so usually file modification history tends to give you very high probability that it's a failure. So we just use that for failures, and then everything else was a flake basically.
Also, was it a real project? Because I don't completely see why would you build the whole machine learning stuff if you can just do it, to look at the test and mark it.
Well, so the idea with that was to find those flaky tests and then tag them and basically have a list of those flaky tests so people could either ignore them or fix them, basically. So this project doesn't aim to actually fix anything. It's just aim to, okay, this is an actual flaky test. You can either ignore it, like ignore, so other people are not bothered by it, or fix it if you want to. Uh, Now, as I said, we developed that while we were at Fitbit and we had like Bitbucket and all of that. Then Google came along and they already have that in place. So our project right now is not relevant, so to speak.
Quick question, like for example, the model that was the outcome of all of this, can it be like, will it work no matter which code base or which company?
Yes.
Like, is it
Y- Yes, I mean, initially we thought about looking at the actual code itself, but that's very hard. I mean, now we can see some progress with ChatGPT and understanding code, but back in those days in 2019, there wasn't any model. I mean, there was something called code to VEC that was looking at actual code, but it was performing pretty poorly. So in this case, looking at the actual history, it works on any code base. I mean, it doesn't matter basically. JavaScript, Swift, Android, whatever. Yeah, I mean, there is public information that Google provided about how you can build that, and basically we built our tool inspired by Google, so to speak, when we were not part of Google. So right now, I don't think there is any. This particular tool is not outsourced. Yes. Okay.